Welcome. Today's lesson is on 4.1, which is exponential functions. We'll be talking about exponential functions, which is probably familiar. We did cover exponential functions in chapter 1, kind of focused on a sequence point of view. We're going to talk about half-life, double life, and have several examples for you to follow. And we will end with graphing some exponential functions. So you might want to have your graphing calculator handy just to take a look at some things and do some calculations. First example is just kind of talking about what makes something exponentially grow or what makes something exponentially decay. So the format you're going to want to be familiar with here is y equals a times b to the x, and knowing that if it grows, your b, you can see down here, is going to be greater than 1, so that's going to give it a ratio of more than 100%. So it might, if b is 2, for example, it might double over time, grow by 200%. And if a is 1, your y-intercept, your initial value, is going to be at 1. You can see that on both graphs. If your base, your rate of growth or decay, is in between 0 and 1, so for example 1/2, then it's going to decline over time, so we call that decay. So when you look at a function that actually has numbers in it, we'll focus on this one down here first. Notice the a value is 2/5. That is always going to be your y-intercept. So a is your initial value, and without any shifting or reflecting, that's going to be your y-intercept. And then b, your base here, because it's 5, which is larger than 1, that's going to be a growth situation. So that one is definitely growth. The second one here, be careful, your a here is a 1. There's like an imaginary 1 out front here that you won't probably ever see, right? And then your base, which is your rate, is 0.4. Since that's less than 1, that's going to be a decay. So that's in between 0 and 1, looks something like this. And the last one, your a, initial value is 8, so that means your y-intercept is going to be way up at 8, so way up there. And your rate being less than 1 is going to be a decay, exponential decay. So they're pretty easy to pick out. Just wanted to give you just a little brief, quick introduction. You could obviously put all of these onto your graphing calculator and take a look at how the graph looks. If it's growing, it's rising from left to right. If it's decaying, it's going to fall from left to right. So that's another option for you as well. All right, our first application question, you might want a calculator handy just to make sure you can do the number crunching along with me. So Miss Milton deposits $3,500 into an account that's going to give her 2.5% annual interest. Mr. Fogarty deposits $3,000 into an account that's going to give him 3.5% annual interest. We talked about these types of questions in chapter 1, so it's been a while. So just a little bit of a refresher. The question is going to ask how much do they have after 10 years. So if you recall, in chapter 1 we did these as sequences. Now we're going to be looking at these as growth. Your money, you put it in a bank, it's going to grow over time if you let it sit. So A is your initial amount. So for Miss Milton that would be $3,500, and for Mr. Fogarty that would be $3,000. B is the growth rate, and you need to be careful with these because if you're going to earn 2.5% annual interest, you want to make that grow, so you have to add 100% to both of these. So when you put these into the equation, this is Miss Milton's, for example, her initial value A was $3,500, and then her interest rate was 2.5%. Make sure you turn that into a decimal. Move the decimal over 2 places. And then you have to add 1 so that her money grows by 102.5%. 2.5%. So this is how her function will look. And then X is your time. So for Miss Milton, I would just put 10 years in for her equation. So hers would look the same, but I replaced the X with 10, and she, after 10 years, would have $4,480.30. Okay, so Mr. Fogarty is going to be the same, except for he has less money initially, but a higher interest rate. So after 10 years, he will have $4,231.80. I would pause the video, make sure you can type these into your calculator, get the correct answer. After 10 years, Miss Milton has more money than Mr. Fogarty. Okay, so obviously that won't happen in the long run. How long until Mr. Fogarty will actually have more money than Miss Milton? So you could approach this a couple different ways. You could set these equal to each other since they both equal y, and you could put x's back in for the 10 because we don't know the time, and you could try to solve for that, although we haven't algebraically explored that yet. So I would look at this graphically, and what I did was I just put both equations into my graphing calculator. Okay, so you can see Mr. Fogarty's in red and Miss Milton is in blue. And off to the side here, I put my window. So I set my x max to 30. Keep in mind, x is years. And so I knew after 10 years, Mr. Fogarty still had less money. So I upped my x max to 30 years just to kind of see a bigger picture. And then I set my y max to $8,000. Y is the money. And I knew after 10 years, they would have upwards of $4,500. So I just increased my y max to a larger value, again, to see the big picture. So you have to think about your window. When I graphed these, I could see the intersection, and then I used my intersect feature on my calculator, and I got the time to be 15.88. So your answer to that would be after 15 years or the start of the 16th year, Mr. Fogarty would officially have more money than Miss Milton. You might reference doubling time or half-life in certain questions. So if you have an exponential decay situation, half-life just means when does it reach the point where it literally cuts in half. So if I started at 8 million, my half-life would be 4 million. And you might be asked to figure out when that happens. I won't go into any greater detail with that. I just wanted to expose you to those words. Doubling time is the same idea, only obviously you would be growing. So if I started at 15 people, when will I double to 30 people? You might be asked to find, but we just might use the words like doubling time instead of when will you double. So nothing too major here. So for example, you'll want your calculator for this one as well. Okay, most cars depreciate as they get older. And if you aren't familiar with the word depreciate, that just means that it goes down. Suppose an automobile originally cost $14,000 and it depreciates by 1/5 of its value every year. Okay, and I'm going to ask, what is the value after 2.5 years? So the tricky thing about depreciation, because you're going down by 1/5, and again, we've talked about this, but if you go down by 1/5, you're going to lose 1/5 of the value. You want to think about your base in terms of how much do you keep. So if I lose 1/5 of my vehicle, that means I'm going to keep 4/5. So when you set up the actual equation here, using the exponential model, you want to make sure you account for that. I used V for value of the car. Okay, so $14,000 is my initial value of the vehicle, and then I did 1 minus 0.2. 0.2, by the way, is 1/5 as a decimal. And so you're going to have 100% of the vehicle, and you're going to subtract off 1/5 every year. So it's kind of logical if you think about it that way. Of course, you could just write 1 minus 0.2 as 0.8 as well. The value after 2.5 years, so I'm going to put 2.5 in for time. That's my x. And then you obviously will need your calculator to calculate that. And I got $8,014.07. And make sure your answer should be logical. Obviously it decreased, so that's a good sign. Okay, second question, when is the car worth half of its initial value? Okay, well, if it started at $14,000, half of that will be $7,000. So you could certainly approach this from an algebraic standpoint and say, well, 7,000 is when it's going to be half, equals 14,000 times 0.8 to the x. Okay, and again, algebraically speaking, I could divide both sides by the 14,000 to try to solve for x. You can't times these because the 0.8 is raised to the x, so be careful with that. But if I divide both sides by 14,000, I get 2. Oh, I'm sorry, I don't get 2, I get 1/2. I'll fix that right now. So I get 1/2. And I want to know when x is going to equal that. So I could pick up my calculator and I could just guess and check. I know that it's going to be more than 2.5 years, right? Because this wasn't quite to 7,000. So I could try 3 and I could try 4. And if I get really particular, I'm going to see that about 3.1 for x is going to make that equal half of its value. Okay, you can also look at this on your calculator. Always. So I could put the original function up here. I could put that into my y equals, and then I can type in 7,000 into my y2, and I can look for the intersection of my model and the 7,000, and I can see that they intersect at 3.1. So that would be after 3.1 years. You don't have to show any algebraic process beyond what I have here. It can be guessing checking if you don't want to graph it, and that is completely fine at this point. All right, now we're going to transition into graphing exponential functions. So I'm going to start with just a basic exponential parent model, and I'm going to use a base of 2 just to keep things somewhat simple on the brain. So if we do y equals 2 to the x, your a is 1, because there's an imaginary 1 out front, so do be careful with that. And then your b is 2. That's your growth rate, so it's going to double over time, right? That's your base. If I plug in some numbers, okay, so for example, if I start down here, if I plug in 2 for x, 2 squared is 4. If I plug in 1, 2 to the first is 1, et cetera, et cetera. Now, be careful when you do negative exponents. If you recall, when I do a negative exponent, I'm going to do 2 raised to the negative second, which means I'm going to reciprocal the base. If you don't quite remember your exponent properties at this point, you could certainly pick up your calculator and do 2 to the negative second. It will give you 0.25, so you will be just fine. If I plot these points, 0, 1, 1, 2, 2, 4, notice as I'm going negative in the x direction, my output values are getting smaller and smaller and smaller. Well, if you think about it, no matter what negative number I put in here, I'm never going to quite reach 0. So as I look at this graphically, I highlighted a couple of my points. As x gets smaller and smaller and smaller, my graph is approaching 0, but I'm never going to quite get there. As x gets bigger, obviously my output y is getting bigger and bigger. So you can see that exponential growth graph, I think, quite nicely. Okay, as you graph these now with shifts, I'm just going to make sure to remind you we covered a lot of transformations in Chapter 3, but the transformation that is with the x-coordinate is your horizontal transformation. So in this case, if you need to remind yourself, you're going to go to the left for, because it's always opposite, because it's x minus h. And then whatever you add or subtract after the x, so in this case I'm subtracting 3, that's going to be a vertical shift, so I'm going to go down 3. And then the multiplier out front, that would be your dilation, so you're going to double your y coordinates as well. So if I kind of type this out, I'm going to double y. I'm going to go to the left 4, and I'm going to go down 3. Those would be my 3 transformations, right? Okay, so as we think about those, if you recall, my recommendation to you with transformations is to do all of your y stuff. So start always with the multiplier. So I'm going to double y, and then I'm going to go down 3, which is also a y transformation. So if I organize, this is my original parent function, 2 to the x, and then I'm going to do this and this and this to all of my points. So I just took 2 key points, 0, 1, and 2, 4, because those are pretty nice points to deal with. And if I think about my transformations, my x is going to the left. So I'm going to take all my x's and I'm going to subtract 4. So 0 minus 4, 2 minus 4. You can see that math from blue to red. And then my y transformations, I'm going to double first because that's my multiplier. It's important to do that. So double my y's and then subtract 3. So if I double 1, I'm at 2, and then subtract 3, I'm at negative 1. If I double 4, I'm at 8, and then subtract 3, and I'm at 5. So when you graph these, you can see, you can't, I didn't highlight them, I apologize, but negative 4, negative 1, you can see that point right here. And negative 2, 5, you could see up here. And the only other thing is, you know how the parent graph was approaching 0, okay, that would be your asymptote. So if you recall, an asymptote is a line that your graph is going to approach, but in this case, it's never going to quite reach that. So if I drew in the asymptote over here, it would be at 0. Well, where do you suppose this asymptote is going to go with all of your shifting? Well, the horizontal shift isn't going to affect it, and the dilator is not going to affect it, but the vertical shift is definitely going to affect it. So if it was at 0, now it's going to be shifted down 3, so you can see that vertical asymptote there. And again, you could certainly look at this on your graphing calculator. Just a standard 10 by 10 window should suffice. If you look at this graph, and I know I don't have the best picture here, but what is the domain of any exponential function? I mean, look at the parent function. It goes on forever to the left, forever to the right. Same thing here, even with my shifts, it's technically going to forever to the left, and it's going to go forever up and to the right. So my domain for this is all real numbers. And if you want to use interval notation, you can certainly do that. You can also use inequalities. I'm sure all of your teachers have talked about the different ways to write it. So if I use interval notation, I would be negative infinity to positive infinity. And or you can use inequalities, that's fine as well. And then the range, I'll give you a second to think about this one. What can y be? Well, notice my graph never goes past this asymptote. So it starts at negative 3, not including it, and then it goes up forever and ever and ever. So my range is going to be negative 3 with a parenthesis through infinity. Through infinity. So if you prefer, you can write that as an inequality as well, and you could do sorry, I can't type and talk at the same time. You could say x is just greater than negative 3. That's also fine. But you can probably tell that your range, in this case, definitely correlates to whatever your vertical shift is. And your domain is always going to be all real numbers. Exponential functions go on forever to the left and to the right.